Welcome to Math Essential Vector Calculus. Today we are with the divergence, which measures how fields spread and converge. Divergence tells us how much field is spreading out as a point. We have an analogy here of electric field and charge. We have two charges, one positive charge in this position and another negative charge in this position. As we can see, field is coming out from the positive charge, forming some loops until it reaches back to the negative charge. So it is spreading out from the positive charge, and using the divergence we'll detect this one, and in this case we name this one source, and when it is converged inward in another location, we'll find that this location is just a negative charge and we name it sink. So let's learn together how to calculate the divergence for a vector field f. We must just multiply the nabla with f. This is the general expression of nabla, and then we make dot f, and then we'll find that we need to differentiate the f in each direction. And if we imagine an analogy, as we learn later in this video, the divergence is just a vector operation which will convert a vector field to a scalar field. And as a recall for you, we have a recap here that the scaling factor h1, h2, h3 can be calculating or expressed as shown in this table. Let's do the Cartesian coordinate calculation of the divergence. We have nabla dot f will be equal to I partial f by partial x plus j partial f by partial y plus k partial f by partial z, where our f or our vector is equal to I fx plus j fy plus k fz. And here we need to remember that this notation here doesn't mean it is a function of x and y and z. Instead, of course, it is each of them is function of x, y, z, but this notation just to symbol it is in this direction, I mean relevant to the I or j or k. And let's do each component together. I partial f by partial x will be reduced to I dot this form here, because this is the sum here, so we can distribute the different derivative in the three directions. And now we need to know how we reach this form here. If we take one, and it will be same for others, partial f by partial I fx by partial x, then we can write I partial fx by partial x plus fx partial I by partial x. We have explained previously in the derivative of the unit vectors, so you can just refer to this table here, but if you want to know more information, you can refer to the other video about the derivative of coordinate system unit vectors. So this means this part will reduce to 0, then this will equal to I partial fx by partial x, and this is what you can find here, and you can repeat for the other coordinate system. Now finally we apply the dot product, and this is another thing which we need to remember together. If you have the same unit vector, dot product will be equal to 1, but if you have I dot j or k, because they are perpendicular, you will have 0. So that's why once you make the dot product, only this component will remain. Then at the end, this will equal to 1, and the other component will go 0 because of the dot product, and you will be left with partial fx by partial x. Likewise, you can do the same for the other components here. I mean component of j and component of k. We will do together. We'll just show here these two components, and finally your total divergence in the Cartesian coordinate will be just because it was here, these three terms, and each of these terms reduced to partial fx by partial x, partial fy by partial y, and partial fz by partial z, and we just sum together to reach the famous, or what you can see normally in the internet or other text box. So let's wrap up. We have learned that divergence measure field outflow at a point. If it was positive, this means it is a source. If it is negative, this means it is a sink. And if it is 0, then no net flux. And divergence converts vector field to a scalar field. And next we will learn together how to calculate the divergence in cylindrical and spherical coordinates. Thank you.